This is Physics 7LC, Week 1, Explanation 1, Overview of Position, Velocity, and Speed. So in physics, our goal is to figure out how objects interact. And we're talking about objects from the smallest scale, like quarks, which make up the nuclei of atoms, all the way to different galaxies and how these two galaxies might interact with each other. But before we can talk about these interactions, we first have to be able to describe objects, locations, and their motions. So we're going to talk today about some terminology that allows us to do this. So the first thing that's really important is to talk about the difference between a scalar and a vector. So a scalar is a quantity that has a magnitude but no direction. And so we have a bunch of different examples that we can give of scalars. Any number that you have, the number 5, the number pi, -22, those are all scalars. If we have a speed, say 100 miles per hour that you clock on your speedometer in some faraway highway, that's a scalar because it doesn't have a direction. If we're talking about a mass of an object, 5 kilograms, that's an example of a scalar. Times, 84 seconds. Time doesn't have a spatial direction, so that also counts as a scalar. The number of cats owned by somebody, even if they have no cats, the number 0 or 0 cats is a scalar. And other examples, temperature, because it doesn't have a spatial direction, that is a scalar. So -20 degrees Fahrenheit, even though there's a negative sign, it doesn't indicate a spatial direction. So that's a scalar. Vectors, on the other hand, are quantities that have a magnitude and a direction. So magnitude, again, is just a fancy word for size. And direction, we're talking about a direction, generally in our class, we're talking about a direction in space. So one important thing is that whenever you're going to represent an object that's a vector, something that's a vector, you always put an arrow over it. So if we're talking about velocity, we always put an arrow. Momentum, we'll talk about later, put an arrow. In books, they often don't put an arrow. They instead make the vector bold and sometimes italicized. But because it's difficult for us to write in handwriting with that kind of font, we always use the vector to make sure we're clearly communicating the thing that we're talking about is a vector. So some examples of things that are vectors. We have a velocity, which gives you a size, like 10 meters per second, but that alone isn't the velocity. We'd have to also specify in the positive x direction or some other direction, and that makes it a velocity. We could talk about just something like 5 miles to the east. That might be an example of a displacement, say how far you walked and what direction makes it a vector. We could talk about 11 kilometers downstream. So again, downstream gives us the direction, 11 kilometers gives us the size. Or we could talk about a force, which we'll do in a couple weeks. The size is 8 newtons, and the direction for the example could be to the left. So we have to be really careful when we talk about vectors to use the rules of vectors addition and subtraction. We in this class use the tip-to-tail method, which says that if you have two vectors, and b, if you want to add these two vectors, what you do is you redraw the vector keeping the same length and direction. So here's vector b, again the same vector, it's supposed to have the same length and the same direction. And the resultant vector of a plus b, it goes from where we started, the tail of a, to the tip of b, a plus b. So if you think of this, for example, if you were to have walked along the vector a and then along the vector b, the vector a plus b gives you your net displacement, the distance and direction from where you started to where you finished. Let's talk now about a coordinate system. So a coordinate system you can think of as a grid in space. So the grid has axes. A lot of times in this class we'll be using the x and the y axes for two-dimensional space. Sometimes we might add in a z-axis. And the place where the axes meet is called the origin of the coordinate system. Now you can choose any kind of coordinate system you want. Let's say that you had some kind of a setting that you're working in, some mountain with the sun. You could choose a coordinate system with your origin at the top of the mountain, like this, with the x and y directions going this way. You could choose it at the bottom of the mountain, like this, and you could choose it so that x and y were perpendicular, but that x was going up the mountain positive, and y is perpendicular to the mountain. You could choose it on the ground, and you could choose this in the opposite direction, such that the positive x direction is going this way and the positive y direction is going this way. So there's all kinds of choices of coordinate system, and in many problems, unless it's given to you explicitly, that choice is up to you. Vector is really important because all of our spatial quantities, position, displacement, then velocity and acceleration, come from the definition of the position vector. So we're familiar if we have, some setting. We might think of our position as the location that we're at, like for example, the top of the mountain. But actually in physics, position is defined according to some coordinate system. So let's say I choose the coordinate system where I have the origin at the center of the sun in my picture. The position vector for the top of the mountain goes from the origin of my coordinate system to the location that I'm talking about, and we give it the vector r. So this is the position vector for the top of the mountain with the coordinate system chosen at the sun as defined here. So position, even though we might think of it as a location, it's always a vector that goes from the origin to the location that we're discussing. Displacement is the change in position. So we give it this symbol where the delta means change. And what it means, anytime you have a change, you just take the value of the final quantity and subtract from it the value of the initial quantity. So let's say you started at the top of the mountain and then you finished at the bottom of the mountain. This would be our initial. Your position vector again goes from the origin to the location that you're talking about, so this is our final. And the position vector is just, the displacement vector, you just subtract our initial from our final. Velocity is defined as the change in the position vector in time. And to be precise, if we're talking about the instantaneous velocity, it's the derivative of the position vector in time. So mathematically, that's how it's defined. You can think of velocity's magnitude as how fast you're going. It's how much distance you cover in a given amount of time, or the change in the position vector magnitude in a given amount of time. The direction of the velocity points in the direction that you're moving. So as we said before, instantaneous velocity is the term that we use when delta t goes to 0 and then the velocity becomes a derivative. We use the term average velocity if we're looking at a bigger time interval. Speed, as we mentioned, is a term that means the magnitude of the velocity. And then the last thing we'll talk about is a motion diagram. So for a motion diagram, imagine that we have some object, say like the sun. And if we are tracking it across the sky from our position, maybe it looks like this. And what makes something a motion diagram is if this picture is taken with an equal amount of time between the first and the second picture as between the second and the third picture. So you can look at a motion diagram, and by the distance between any two successive images, you can get an idea of the average velocity between those two times. If we were to include on this diagram some vectors that indicate the velocity at various times, then it would look like this, and we would call it a velocity diagram.